Today we are going to talk about the last topic that is going to be covered in this chapter, and that is going to be indeterminate beams. If you remember, we have already talked about indeterminate elements in the axially loaded elements and in the torsional elements, two elements that we have already talked about in mechanics of materials. The third element that we talked in this course is beam. We want to conclude our discussion by understanding how to analyze indeterminate beams. So today, we want to see what are indeterminate beams and how can we analyze them in order to determine the reaction forces and internal forces. We have already talked about the concept on the video, so I'm going to review the basic concepts of indeterminate beams, present some examples, and then we are going to practice some problems. First of all, indeterminate structures stands for the cases where we cannot determine the reaction forces or internal forces just by equilibrium equations. This is the general definition that we have used before, whether it was axially loaded elements, torsional elements, or beams. In particular, for two-dimensional beams, there are three equilibrium equations that we can use. First would be sum of the forces in the x direction. Second, sum of the forces in the y direction. And the third one, sum of the moments. So as long as there are three unknowns or three reaction forces, we can determine those just by equilibrium. If the number of reaction forces is more than three, then the reaction forces cannot be determined just by equilibrium, like the case that we see here. In this case, there are three reaction forces on the left support and one reaction force on the right support, which means that the total number of reaction forces would be 4, but we do have just 3 equilibrium equations. That makes the problem impossible to solve just by what we have learned in statics. So we call that statically indeterminate structure. By the way, the number of reaction forces depends on the type of reaction support that we have on the structure. For pen support, there is just one unknown, one reaction force, which is perpendicular to the element, as shown here. For the pen support, there are 2 reaction forces because the beam is restrained in 2 perpendicular directions. It is restrained in the horizontal and vertical direction, which means that there are 2 reaction forces in these 2 directions. And for the fixed support, there are 3 reaction forces. So depending on the type of support on the structure, we can identify how many reaction forces there are, and based on that, determine the degree of indeterminacy. How can we analyze indeterminate structure? If you remember, previously, we took 4 steps to analyze indeterminate torsional elements or axially loaded elements. Here, we're going to do the same. Steps are going to be the same. There are some differences in the way we calculate the deformation, but the basic concepts would be the same. So the very first step would be releasing the redundant supports. So for this case, there are 4 reaction forces and we have 3 equilibrium equations, which means that there is 1 redundant support. Which one do we want to release? It is up to us. We can release whatever we want to release, but in some cases, it is easier to release a certain support. For this particular problem, I think it would be easier for us if we release the pen support, the ruler support at B, and then replace that with 1 unknown force. Then we are going to split this structure into simpler cases. In this case, there is 1 external loading, the distributed load, and 1 reaction force. So I'm going to split this structure into 2 components. Each is subjected to its own force. The first one is the beam subjected to the external distributed load, and the second one would be the same beam, but now this is subjected to the reaction force. Now, we need to go to the third step, in which we need to determine the deformation at the point that we have released our structure. In this case, we have released our structure at the very right end, so I have to determine the reaction force at the very right end of this beam. How can we do that? This is a big topic that we have already talked about, how to determine the deformations in different beams. There is a hint. I said determine the deformation at the released support. Deformation means the way the beam is moving, deforming, displacing, right? In beams, we have 2 types of deformations. One of them would be movement of a certain joint. The other one would be rotation of the beam, which is shown by slope. Which one should be determined? It depends on the type of support that we have released. If we are releasing ruler or pen support, we need to determine the deflection or delta, the displacement of that point. If we are releasing the fixed support, then we need to determine the slope of the beam at that point. For this particular problem, we have released the ruler support, which means that we need to determine the deflection of the beam at point B. All right, after we determine the deflections or deformations of the beam at different points, then we need to find out what would be the relationship between the deformations in the structure. Again, for this particular problem, we know that the beam is supported at its right end, which means that the right end should not move. In other words, the deformation that we see in these two beams should add up to 0. The downward movement of joint B in beam number 1 should be equal to the upward movement of joint B because of this release support. Then I would just write down the compatibility of deformation, and that gives me the extra equation we need in order to solve the reaction force for this structure. Okay, again, this is a topic that we have already talked about, but I just wanted to kind of briefly review the concept and then solve one problem, because this topic, similar to the other indeterminate structures, is possibly one of those difficult topics that we have by the end of each chapter. Now let me give you one example. There is a beam that is subjected to just one force P with distance of A from the left support. In this beam, we have a pen support at A and 2 ruler supports at B and C. This structure is obviously indeterminate because there are 4 unknowns, or 4 reaction forces, 2 at A, 1 at B, and 1 at C. The number of equilibrium is 3 in 2-dimensional beams, which means that this beam is a 1-degree indeterminate, which means that we need to get one extra compatibility of equation in order to solve this problem. Based on the steps that we talked about, we can release any of these supports that we want, but one of them is probably easier than the other one. For this particular case, which one is easier to be released? B is easier. The reason for that is if I release this support B, the beam is going to be simplified into a simply supported beam, which we already have a table that gives the deformation of that beam. So it is much easier than the other cases, like removing C or releasing one of the forces at A. So I'm going to remove B and replace that with one unknown force. Then we need to split the beam into 2 simpler parts. The first one would be the beam subjected to just that external force. The other one would be the beam subjected to the reaction force at B. So we have split our structure into 2 parts. Then we need to determine the deformation in each of these 2 parts. First of all, I'm going to determine how much is the deformation in beam number 1. Remember, we need to determine the deformation at the point that we have released our structure, which is point B. I'm going to go to the course website and pull up the beam deflection table to read the value of deformation for that beam. So I'm going to go to the references, equations, formula sheet. By the way, make sure to print this, including the last 2 pages that has the beam deflection table in the exam, because you are going to need that in order to calculate the deflections. So we have this beam, and the only matching beam that we can use would be this case. In this case, we have a force of P acting on this structure. Distance of that force to the left side is shown by A, and distance of the force to the right side is shown by B, and the total length of the beam is L. We are interested in determining the deformation at a certain point, which is not necessarily the maximum deformation. So I'm going to use the elastic curve, which gives the deformation at an arbitrary point specified with distance of x. X is the coordinate of the point at which we want to determine the deformation. But there is one important condition that we have talked about that before. This equation is valid only if x is between 0 and a. Okay? Now I'm going to get back here. I'm interested in determining the deformation of this beam at point B. If I measure x from the left side, x would be a plus b, which is 3 feet plus 5 feet. That would be 8 feet. And a, if it's measured from the left side, that would be 3 feet. So x is going to be larger than a. That equation is not valid. How can I resolve this issue?
Look at it from the other side.
Right, flip it. Okay, so we are going to flip that structure and measure the distance from the other side. So I'm going to use the same equation that is shown here, but I'm going to flip A and B. And by the way, we have A and B on the table, and we have A, B, and C given as the problem parameters. So in order to avoid confusion, when I write down the equation from the table, I use subscript of table for B and A to separate them from A, B, and C that we were given in this problem statement. The length of the beam is going to be the total length, which is A plus B plus C. That is going to be 12 feet. X, as we discussed, is going to be measured from the right side in order to maintain the condition, which is X should be smaller than A. So X is going to be measured from the right side, and A in the table is measured from the right side as well. So that would be B plus C. And B on the table would be the distance of the force to the left side, which is equal to the A that we were given in this problem statement. All right, now I just need to plug in the values, and that would give us 0.01014 feet. Okay, I didn't need to do any unit conversion here because all of the parameters are given in kips and feet, so I just plug them in. This guy here is going to be 5 feet, so that is not meter. Okay, now we need to determine the displacement in the second beam at point B. In order to do that, we are going to go back to the table and calculate the deflection at that point. In this particular case, because we are going to determine the deformation right where the force P is acting on, this deformation is going to be the maximum, so I can use the simplified equation, PA squared B squared divided by 3LEI. Again, to avoid confusion, for A and B that we read from the table, I use subscript table in order to separate that from the parameters given in this problem statement. We have P, which is unknown, is R sub B. All other parameters could be calculated. So I will write it as a coefficient K multiplied by reaction force. And K is simply A squared B squared divided by 3LEI. All right? Now let's calculate that K coefficient factor. A, in this case, is going to be the distance from the left side, A plus B, which is 8 feet. And B in the table would be the distance of the force to the right side, which is C, which is 4 feet. Now we are going to plug in the values, and K would be equal to 0.00045. All right, the last step is determining the reaction force using the compatibility of deformation. What is the compatibility of deformation in this case? How much is the total deformation of this beam at point B? 0. The beam is not moving, it is restrained. So sum of the 4 deformations in these two cases should be equal to 0. Depending on the direction of the forces that are shown here, the deflection of the beam is going to be downward because of external force P, and it is going to be upward because of this reaction force. So one of them would be positive, the other one would be negative. Which one is positive, which one is negative, it doesn't matter. We just write down the difference between these two deformations should be equal to 0. Now we are going to plug in the values, and from that, the reaction force is going to be delta B1 divided by K. Plug in the values, give us 22.53 kips. So this is going to be the magnitude of the reaction force using those 4 steps for analyzing indeterminate beams. Again, what I want to highlight is the similarity of those 4 steps that we have used several times in order to analyze indeterminate structures. Okay, any question for this problem? Yes. Okay, good question. So the question is, on the exam, in particular on the exams, do we need to derive the equations in order to determine the deformations in the beams, or we can use the tables? On the exams, all the problems could be solved just by using the equations on tables. In the real world, no. The beams in general cannot be just solved using those limited cases that we have on the table. But on the exams, we don't have enough time to derive the integration and then calculate the deformations. All right, now I'm going to open up one practice problem for you. In this problem, we want to analyze this structure, which is obviously indeterminate, and we want to determine the amount of reaction force at the middle point. I want to solve this problem in two different cases. First, in the case shown here, so there are 3 supports. In case B, this ruler had settled down by a certain value. So because of the force, this middle point, this middle support is not totally fixed. It is settling down by a certain value. I want to determine how much would be the reaction force in that problem. Yes. We can assume that the roller itself is deforming or being compressed, or we can assume that the entire roller is moving downward. In the reality, it happens in some structures where the soil underneath structure is not strong enough. So sometimes we have uneven settlement of the soil, which is actually causing a lot of issues because there will be distribution of forces within the structure that are not intentionally designed, that may increase force at a certain part of structure, which may cause damage. So probably you have seen sometimes there are some cracks on the walls, and that is possibly because part of structure is moving down, other parts are staying there, and that unbalanced deformation is causing internal forces. So this is kind of simulating that. 2 teams reached to 100%, so 2 and 3 are going to receive that extra bonus point. And again, I can't emphasize how important is the activity and discussion. This is not about point. This is not about getting 1 point or not. This is about learning from each other and interacting with each other. So in order to solve this problem for the first part, we simply need to determine how much is the deformation of this beam subjected to the distributed load at the midspan, which would be its maximum. So I just go and calculate the deformation, which would be 5WL to the 4th divided by 384 EI. And then calculate the deformation in the simply supported beam where there is a reaction force at the midspan. The deformation in that case would be PL cubed divided by 48 EI. In case A, sum of these deformations should be equal to 0, which means delta 1 minus delta 2 is equal to 0. From that, we can determine how much is the reaction force. That would be the answer for the first part. For the second part, it is a bit more tricky, because in that case, that support at the middle part has settled down. So the only thing that is changing for this case versus case number 1 would be the compatibility of deformation. Now, instead of having delta 1 minus delta 2 equal to 0, we have delta 1 minus delta 2 is equal to the settlement of the support at that point. That's the only difference. All the equations are going to be the same. So that is going to change the magnitude of the reaction force at that point.